Chris. Yeah, so this is a project I'm on with the consortium. The consortium name is the Crash Avoidance Metrics Partnership. This is a group of 8 auto manufacturers of whom I can name. It's here on the slide. They've partnered with TTI, again, where I'm from. We have University of California, Riverside on the project to help with some emissions. And we have Umtree on the project to provide further help with infrastructure analysis. So here is my disclaimer. This project is funded by FHWA. I don't necessarily present their opinions. So today I will be talking through what Tosco is. Tosco stands for Traffic Optimization for Signalized Corridors. You might look at me and say, David, we already tried to do that. To which I'd say, yes, I didn't come up with the acronym. Tosco, it's a system that's working between the infrastructure and the vehicles using the connected vehicle DSRC technology. I'm going to describe the simulation setups at a very high level today, and covering some of the different things that we've done to make this work. So I'll talk through the simulation we have for vehicle development, the simulation that we have for analysis of this system on a corridor, some of the challenges we've had along the way, and our next steps for the project. So what is Tosco? Well, the first component of Tosco is the infrastructure. The infrastructure essentially, the text is a little bit small there, but the infrastructure essentially uses information from the vehicle detector where's the pointer? There it is. It uses information from the vehicle detector to calculate queue information. Is that working? Yeah. Calculate queue information in the algorithm, and it also uses information from the signal controller to kind of come up with that signal phase and timing. What the algorithm then does is it uses that queue and signal timing information to provide essentially a recommendation for vehicles on when to arrive at the intersection when the signal is green and the queue is cleared. This is on a by-lane basis to help these vehicles plan their approach. And so this information is transmitted over the air to the vehicles. They receive it on their onboard unit, which is of course transmitting BSMs, which the infrastructure might use to refine its algorithm and refine its estimation of when the vehicles should arrive at the intersection. And it uses driver input. So this is really a driver assist technology. It's not autonomous per se. The driver still has to manage their position within the lane. But what the Tosca algorithm does on the vehicle end is it takes this driver input and the information from that infrastructure and produces acceleration and brake commands for the vehicle. What it does, and I'll explain this in the coming slides, is it's operating in a platoon, and what it'll do as it approaches and comes within communication range of that intersection is it could choose to maintain constant speed. It might speed up at the intersection. It could slow down under some circumstances, and preferably, it would rarely come to a stop, where if a stop is inevitable, all the vehicles would stop simultaneously, then pick up speed simultaneously. So what might that look like? Well, essentially, as a vehicle is entering communication range, they have this area within the time that they enter communication range and the time that they cross the stop bar. We call that the approach speed optimization zone. This is where they're really trying to decide, what am I going to do as I come up to this intersection? And as they cross the intersection, we have the coordinated launch zone. That's the area that they are recovering their speed to their set speed as they go through the intersection. So the one scenario, we call it the speed up scenario, right? This is when the vehicle enters communication range with a set speed lower than the speed limit. And what the vehicles would do as they come into communication is they would gain their speed, and the idea behind that is to allow traffic behind this vehicle that for some reason decided to go less than the speed limit, give the vehicles behind it an opportunity to get through the intersection, essentially increasing saturation flow rate, to use a traffic engineering term. The other alternative to speed up that really isn't in the slides here, but what's possible is if the vehicle's set speed is above the speed limit, it would actually bring that speed down to the speed limit. So if I were naming this scenario, I might call it the adjust to speed limit scenario, right? But the idea is to allow more vehicles to pass through if possible. The other alternative is a slow down scenario. And what this scenario encompasses is a situation where the signal is perhaps red when the vehicle comes within communication range of that intersection. but it's about to turn green, and maybe there's no queue at this intersection, right? And so the signal is about to turn green. The vehicle has the opportunity to bring its speed down, but not come to a stop. And so it could go through and maintain speed as it crosses the stop bar. And preferably, the least common scenario, right, for this optimization function, if you will, is a coordinated stop scenario, where if a stop is inevitable, the vehicle would bring its speed down gradually, stop for a shorter amount of time, and then pick up speed once the signal turns green. At the very least, this would reduce the lost time. Again, use another traffic engineering term. When the signal turns green, the vehicle will be able to respond automatically, given driver confirmation. So again, this algorithm does utilize some level of platooning. It uses the platoons. These are formed ad hoc, kind of like what Mike was talking about, where the vehicles there's not a planned platoon per se. And what they do is, for the coordinated stop, they would all come to a stop together. For coordinated launch, they would all begin moving simultaneously. That is using a distance-based gap in the beginning. And then as they pick up speed, they would transition to a space gap, a time-based gap, and continue to accelerate up to the set speed of the lead vehicle. So talking through the different simulation environments, again, like I said, this project encompasses both the development of this vehicle system and the assessment of the vehicle system. So I have 3 different simulation environments described in this slide. Today I'll be discussing 2 of them primarily. The first one I'll discuss is the vehicle simulation environment. That is the environment that we are testing the actual vehicle algorithms operating these Tosco vehicles within the Vissim environment. The other another simulation environment we use for this project is the infrastructure simulation environment. That is the environment that we use to identify what our infrastructure algorithms would be to provide those estimations for the Tosco vehicles as they approach the intersection. The results from these 2 components, if you will, fused together into the performance assessment environment, which I'll refer to as the traffic level environment. Again, not my term really. But we have the traffic level environment that we use to produce the potential outputs, potential benefits of this Tosco system. So the vehicle level algorithm actually communicated between 3 different computers. The software used in this, the first computer was called the development environment. It had a software on it called the ADTF. That is a German acronym. I don't speak German. I'm glad I don't know what the words are per se, because I don't think I could pronounce them. Maybe Lucas could help me if I did know what they were. This ADTF, essentially what it did is it housed the Tosco code, and it passed the data between what are called filters to maintain data flow, right? And so what this did is it tricked the Tosco algorithms into thinking it was operating a real vehicle. But of course, there's a lot of information that goes into that. So the second computer, the simulation environment as named here, hosted Simulink, which we use to calculate all sorts of information to feed into this Tosco system. It utilized some information from Vissim and calculated other information such as the inertia of the vehicle, the radar component, GPS drift, as the vehicles tried to position themselves within the lanes. There was communication delay modeled in this simulation environment. And this computer was also primarily responsible for synchronizing the data flow between these 3 computers. And the last computer has the product that we are all probably most familiar with in this room. It hosted Vissim. This utilized the driver model DLL to pass information to the Simulink computer. It utilized the ASC3 software controller API to produce SPAT information to feed into that infrastructure component that I referenced earlier. So this was the virtual driving environment. It hosted the traffic light. It essentially used public transit lines to generate the vehicles, to feed into the Simulink environment, to trick the ADTF into thinking it was a Tosco vehicle, and communicate all that information back to Vissim to conduct these tests for the vehicle. So what were we testing? We were essentially testing those 4 algorithms, right? And so first we would define which of those speed profiles we wanted to refine further, identify what we're looking for, create a set of parameters, and there was another piece of software that one of the team members developed to cycle the simulations through all the different options that they explored for the scenario. They would run those simulations overnight. This vehicle level simulation ran extremely slow. And it would produce information for that. A lot of this information was broken down into what operating modes the vehicles were using. It would communicate the time delay. There was all sorts of performance measures generated in this analysis environment. Those would, of course, be reviewed by the engineers. They would identify things that they liked, things that they didn't like, produce a refinement, and then repeat. So essentially, what this environment enabled was an ability to test a vehicle algorithm without needing a real vehicle. They were able to test how Tosca was working and do early refinement before producing field tests, which if anybody's done field testing, they know that field tests are hard to replicate. These simulations had no such issues. And one of the key findings of this vehicle level environment was that the initial speed profiles we started with in this project were insufficient. Essentially, the initial speed profiles we had assumed a zero acceleration, which as we went through edge cases discovered that if the vehicles ever needed to change their, or ever say change their mind, if you will, that would lead to the vehicles violating some of the rules that we had in place for the system. So there's continued testing ongoing as we're moving forward in the project to develop this algorithm further and teach those Tosco vehicles how to do what we want them to do. So now I'm going to transition to talking about that assessment environment. We called this the traffic level environment. What we did is we worked or we analyzed a corridor in Conroe, Texas, which was just north of Houston. If you're familiar with the area, I know Jim is. He's familiar with I-45 that goes between Dallas and Houston. And so we have that interstate along here. State Highway 105 kind of connects up to College Station, where Texas A&M is. Along this corridor, there are 15 intersections, 3 timing plans, and across 12 miles. The posted speed limits on this intersection range from 45 miles per hour on the east end to 55 miles per hour on the west end. Most of the corridor was at 55 miles per hour speed limit. So this is a pretty high speed facility. We simulated the analysis for AM and PM peak scenarios using a 2-hour peak period and market penetration rates of 0, 30, 60, and 100. The setup for the traffic level environment was a little bit different. We only needed one computer. Now this computer still needed to pass information between the driver model DLL for that. In this scenario, the driver model DLL hosted the Tosco behavior. And it passed information within Vissim. We use the emissions model DLL to do a moves output of the emissions results for the vehicles as we went through, because emissions was one of our performance measures. We promised to use moves and we delivered. We used the ASC3 traffic controller in this environment to produce a SPAT information just like we did in the vehicle level simulation. Since we had more than one intersection in this environment, we need to organize that SPAT data and come up with a way to map the bytes that we receive from each controller to which intersection they belong to within the simulation. This fed into the infrastructure algorithm that produced those estimates for when the vehicle should arrive and repeated, right, went through the simulation. We utilized signal timing plans provided by the city of Conroe. We collected turning movement counts at each intersection to feed into our volumes, and we calculated several data. We did several studies to calibrate the model. We did a travel time study, make sure that we have realistic travel times on our simulation. We did tube counts at several cross sections along the facility, make sure we have similar volumes. And we did an acceleration study after some initial simulation. And this could probably be a presentation in and of itself. If you see me at TRB, ask me about it, because that will be what I'm there to talk about. Nonetheless, the acceleration study was really based off of some of the initial outputs we saw. When I showed my auto manufacturer friends this plot, they looked at me like I was crazy. I didn't really understand why, but they said that this acceleration plot, this red line here, that non-Tosco vehicles behaved as they accelerated from a stop was aggressive. They said that'd be like sitting in a rocket taking off. I looked at them kind of strange. This blue line is the Tosco vehicles by comparison. You see that the default vehicles got up to speed much faster than the Tosco vehicles. And so, being the researcher that I am, I said, well, why don't we go out and collect some data? And so we collected some data to represent the acceleration behavior along State Highway 105. This, of course, required us to recalibrate and rerun the analysis. So the acceleration profile, this top graph here shows the acceleration, the default acceleration profile for the vehicles, baseline vehicles in this environment. Again, those seem kind of aggressive. And the concern was that we were having artificially high acceleration for our non-Tosco vehicles. And so we equipped equipped two vehicles with some accelerometers. Graduate student and I went out and drove up and down the road all day, collected 89 speed profiles that we then, well, I say we, my graduate student then compressed into some smooth graphs, produced an acceleration profile to represent the desired speeds of vehicles on State Highway 105. And that is the lower graph here, the graph that we have. You can see that it's a very different shape. Vehicles at a lower speeds start off with a lower acceleration, build up at some point near about 10 miles per hour, and then their acceleration wanes off until they come up to their desired speed. So this is what we use to represent the desired speeds of our 55 mile per hour facility. And so we smoothed it out and utilized it. So then we decided to graph this new line along the rest. Oh, it is showing up great there. Cool. We have this yellow line here of our revised behavior. And what we noticed is that the Tosco vehicles were still a little bit slower. Another sign that we would need to rethink our acceleration profiles for these vehicles. So we're now seeing it in both environments, right? This revision of the non-Tosco vehicles it's a little bit easier with my auto manufacturer friends. So we decided to proceed with the analysis for the AM and PM peak scenarios. We collected all sorts of performance measures. I only have time to go over a few today. This is the results for the AM peak scenario. I call it moderate traffic. There really wasn't any capacity problems in the AM peak. What we see here, the blue lines represent total delay, the blue bars represent total delay, the red bars represent stop delay. You can see that in both eastbound and westbound directions, the total delay increases as market penetration rate goes up, and the stop delay steadily decreases as market penetration rate goes up. And we actually somewhat expected these results. We know that Tosco's primary function to help vehicles avoid a stop at the intersection was to reduce their speeds. So again, reducing speed would naturally increase your delay slightly. And so Tosco's main objective, again, was to avoid stops. And so when we saw these drastic reductions in stop delay, we concluded essentially that Tosco's kind of doing its job here. Then we look at the PM peak results. We didn't have time to do as many runs with this, but what we saw initially, what we see initially here, is that the PM peak scenario, we saw reductions in total delay and stop delay. Stop delay still goes way down. Total delay starts to reduce. And I said, or I made the claim, that this was because we increased the capacity using the vehicle's platooning at the facility. And I was asked to prove it, to which I said, okay. And so I produced a plot of the average queues across time at one of our intersections, Old River Road. And what we saw here was that by the 30% market penetration rate, we were able to stop some of the residual queues that we saw for a long time. So to explain this graph here, this was the average queue length of eastbound traffic at this intersection. We saw queues up to 1,400 feet, and it lasted for about an hour until the demand really went down and the intersection was able to recover to an undersaturated state. these graphs along the bottom here are the queues for the 30%, 60%, and 100% Tosco market penetration rate. So you can see that when we had the 30% market penetration rate, we were able to essentially extinguish that queue. We don't know where in between 0 and 30% market penetration rate that occurs. We'll be searching for it soon. To summarize the conclusions that we had from this traffic level analysis, is that in light traffic, moderate traffic, in that AM peak scenario, Tosco increased, or it reduces stop delay, a number of stops, but it increases total delay. This was primarily because the Tosco vehicles accelerated slower, as we saw with the acceleration study, and that they would slow their speed limit if necessary, or slow their speed to the speed limit if necessary within communication range, because auto manufacturers didn't want to design a vehicle that exceeded the speed limit. In heavy traffic, in the PM peak scenario, we saw that the platooning behavior and the coordinated launch behavior for Tosco vehicles aided in reducing total delay, stop delay, and number of stops, which was great enough to overcome the increases in total delay that we saw in an undersaturated scenario, if you will. And so these results proved to be good enough to move on for phase 2. But before I talk about that, let me talk about some of the challenges that we had along the way. I mentioned time synchronization between the software and between the computers. That was a reoccurring problem within each environment, because if the infrastructure software thought it was one time and forgot to send information to the driver model DLL, the simulation would crash. And so we encountered many different errors trying to pass information back and forth between the software and back and forth between the computers, and making all of them agree on what time it is more challenging than you might think. We also ran into issues comparing the Tosco behavior to the baseline traffic, like I mentioned, doing that acceleration study and trying to figure out what are those baseline vehicles actually doing, is it reasonable? And calculating unique performance measures. I mentioned calculating printing out the operating modes in that vehicle level simulation. That required producing all sorts of files to output data and unique data, using speed trajectories to look at the vehicles, and searching for signs of oversaturation in intersections. So moving on to phase 2, we are refining the vehicle algorithms further, adjusting those speed profiles and how these vehicles act. We're moving on to a field deployment at our Relic intersection. We have a gorgeous picture of a Texas sunny day here out on our runways. You can see our little traffic cabinet and the TTI car, and see our span wire installation. We have plenty of space here to do testing of the Tosco vehicles at a closed course. And so we're integrating, so we're refining it and deploying it on the vehicles so that we can test it in the field. We're integrating these refinements into the traffic level simulation, and maybe I'll be here to talk about it again some other day about how we're doing that and working on getting the Tosco behavior refined in this traffic level environment. And given funding from FHWA, we'll be deploying this on State Highway 105 moving forward. So I know I covered a lot and I barely skimmed the top, but are there any questions today? Yeah.
So did you also check at the throughput from that intersection? Did it decrease, or how was it affected?
Yeah, the question was, did I look at throughput at intersections with increased capacity? And that was actually my first thought, to look at the throughput. The surprising thing is we only saw a few more vehicles per cycle. The cycles were about 2 minutes long. We had it broken down into 3-minute increments. And from a traffic engineering standpoint, it's okay, well, maybe the demand was only 3 vehicles, because queues build up. You kind of saw at the beginning of the plot here, after our warm-up period, the queue was building up quite a bit. And that could be a few vehicles per cycle that was building up. So maybe early on here in our warm-up period, we only needed 3 more vehicles to get through that intersection to reduce or to prevent an overcapacity scenario. So throughput wasn't as exciting of a graph as queue length. That's the answer in short. Queue length is a whole lot more exciting to look here and say, wow, we had 1,400 foot queue that we brought all the way down to like nothing. Throughput is like we got 3 more vehicles
What
through.
section did you use for queue length and delay? Like how upstream did you go from the intersection? Was it from like previous intersection?
Yeah, we calculated the delay across, well, we used node results to look at the delays per intersection, and we calculated delay for vehicles going through the entire corridor. Both were about similar plots. Yeah, Joe?
So with the DLL changing the desired speed, did you look at like total travel time as well, or vehicle hours traveled? Because delay is really set at decreases over the desired speed, so if your desired speed's coming up, that decrease isn't necessarily quantified.
Yeah, that's a great point. We did look at total delay. Like I said, I didn't include those graphs today. It took about 15 minutes to get through the intersection, and you had about 1 minute of travel time savings per vehicle in that PM peak scenario. And conversely, about a 1 minute increase in travel time in the AM peak scenario. That was a trade-off. To avoid stopping, it took you a minute longer to get through. Yeah.
Alex?
I'm wondering if you had a look into the signal timings on their own. We did similar experiments a long time ago. At that point, the concept was called LOSA, Green Light Speed Advisory, and we did this in Vissim, I think even before connected module was there. And you would get a certain type of benefits if you use that progression and information for the vehicles, when to stop versus when to go. But then we compare that to regular retiming processes to kind of see, and then what happens if you actually combine. And we figure out that the benefits are highest when you first optimize your signals, then you use this on top of the optimization. So I'm wondering if you went already in that direction, or maybe you have plans to do that in the future.
Right. So retiming the signals is really outside the scope of the project, unfortunately. We did not want to bother the city of Conroe too much with saying we're going to deploy all this random stuff on your corridor and change your signal timing. We decided to just stop it at, hey, we're interested in deploying stuff on your corridor. So we didn't look into different signal timing plans for this project, but I agree. It might make more sense to change the signal timing as opposed to investing in a system like this.
I don't think it's either or. Actually, when you combine, maybe you get something extra.
Yeah, that's a good point. When we combine them, we might see more benefit. Yeah, if I might add.
No, keep going.
Okay.
Young lady had a question as well.
Sure. Well, one thing, since we talked about the driver model DLL a little bit, I noticed I was a little bit surprised even at how few people are using it. This is a very powerful tool. And if a civil engineer like me with very limited coding experience can figure it out, I would encourage others to look into it when they're looking into altering vehicle behavior for connected and autonomous vehicle applications. But, next question.
I was just curious why it was such a priority to reduce stops. We saw an increasing delay in the AMP, and why is it such a priority to slow cars down so that they don't have to, or they have like minimal wait time at the signal? What's the difference between just having them wait longer?
Yeah. So the question was why reduce stops as our optimization function, essentially. That answer comes with a story. To say it in short, this system started as an eco approach and departure system. And so the mindset was if you maintain speed, you don't use as many emissions. We found that at the higher speed corridor that TTI analyzed, that was not as much part of the story. At lower speed corridors, you do see more emissions impacts. So really to describe the system as a whole, what was consistent between both low and high speeds is reductions in stops and stop delay.
If there are more questions for any of the presenters today, they'll be around today. Of course, you can email them to us. I want to thank everybody who presented today on this very important topic. Nice to be represented by research, by our consulting community, and by the automotive group. So let's give everybody a real hand here today.